Welcome to Apples to Orbits. This is going to be a class where we talk about the concept of general relativity, basically a geometric description of gravity, which was pioneered by Einstein at the beginning of the 20th century. It's a very elegant theory, and we hope that you enjoy it. This is going to be a largely discussion-based class. We sort of believe that it's very nice to be able to talk through ideas. And I mean, I think I personally find that like a lot of the ideas of GR are very, not so hard to, intuit, and that it's easy to believe things a lot more if you can try to figure them out yourselves. And so in the spirit of that, if you're at all comfortable, we prefer it if you turned on your cameras. Just sort of adds to the rapport that would usually be there if we were teaching in person. Of course, don't feel like you need to do this, but it would definitely help the discussion along. Also, don't be afraid to ask any questions or say anything that could be wrong at all, because when we start learning physics, we sort of have this idea that everyone knows more than we do, or a question we have is dumb, but there are no dumb questions, right? Like Einstein, as much of a genius as he's portrayed to be, and as many contributions as he's made in physics, himself took 10 years to figure this theory out. So if he took 10 years, we can surely take a few more minutes to try and understand things better. So before we begin, I would like to just sort of check in on, where you guys are all from and stuff. So if you could, so in the chat box, don't press enter, but could you type in your name, let's say your name, your grade, your pronouns, and what you're excited to learn about. And on the count, I'll give you like maybe a few seconds, and then I'll count down and have you guys all type them in at once. So once again, your name, your grade, your pronouns, and what you're excited to hear about. Okay. Let's do it on the count of 5. So 5, 4, 3, 2, 1. Press enter. Awesome. Nice to meet you all. It looks like you all are very open-minded about what you want to learn from this, which is fantastic. So let's see if there's anything else. Oh, also, so my name is Nicholas. I'm a physics graduate student, and I study stellar astrophysics and the oscillations of stars. And Sarah?
Sure. I'm Sarah. I'm also a physics PhD student, and I'm studying black hole simulations.
I'm Isaac. I'm also a physics PhD student, and I study merging neutron stars and neutron stars in general. Learn more about that today.
What's a neutron star, Isaac?
Nicholas will tell us what a neutron star is.
All right. I think we're ready to get started then. Let me share my screen first. All right, can you all see that okay? Okay, great. Oop, let me just move all these windows. Zoom's interface is pretty clunky. All right, so before we talk about general relativity or gravity or anything abstract like that, let's just talk about your everyday experiences. So you may have seen something fall to the ground once. You may have seen an apple fall once. I don't know. I guess maybe that's not something that happens often these days. But let's say you're watching an apple fall to the ground, and it starts some height from the ground that we will call Y. It's a nice letter. And let's say you're very bored and you have a very good camera. So you take snapshots of the apple falling that are equally spaced in time. What you'll notice is that the apple speeds up as it falls. So it'll start at some height, and then here, let's say it starts up here. And then 1 second later, it'll be down here, let's say. And then 2 seconds later, it'll be down here. And it falls faster the more time passes. Let's just say phases to the ground or something, I don't know. And if you take all these points in time and you plot them, so let's put time here and let's put the height of the apple at a snapshot here, you'll find that you get a curve that looks something like this. So the key thing to notice here is that even though the apple falls in a straight line in space, if you take a look at its path in space and time, or as we like to call it, space-time, it actually follows a curve. And more specifically, it follows a parabola, but that's not important. The point is that it's not a straight line. Now, let's do this experiment again, but in space instead. Let's say that, I don't know, God or whoever you subscribe to just puts an apple in the middle of space, away from the influence of any planets like Earth or any stars. So there's no gravity and it's just floating in space. And maybe it's moving at a constant velocity, or maybe it's just staying still. But either way, you set up your space camera, that's no big deal. And you take snapshots again that are, again, evenly spaced in time. So if the apple is just sitting still in space, I guess I have to make it look like space. Yeah, that looks like space. Okay, so the apple could just be stationary. And in that case, all of your snapshots will look the same. Or the apple could be moving in some direction. But because it's away from anything that could be exerting gravity on it, it'll be moving at a constant velocity. So let's say it's moving in this direction. And you take snapshots. You get snapshots that are evenly spaced like this. The apple won't be speeding up or slowing down. So I guess later it'll look like this. Later it'll look like this. And if you plot what the apple is doing this time, take a look at the trajectory it takes. The apple that's stationary will be traveling in a straight line in space-time. So let's just say you took a bunch of snapshots. You were waiting for the apple to do something and it didn't. That's too bad. And for the apple that's moving, I guess it would be going, it would look something like this. It would also be moving in a straight line. That's not a straight line. Okay, that's even worse. Okay, sure, that's close enough. And this will happen no matter what direction the apple is moving in. So you could have another apple moving, say, this way, and same thing. Maybe I should draw the line, but I guess the line would actually look the same in this case. Or, it could be moving in this direction or this direction or this direction, but it'll be moving at a constant velocity. So no matter what it does, it'll just move in a straight line because there's no gravity acting on it. So the key point here is that gravity is causing the apple to curve. And that's what gravity does to objects in general. Gravity causes things to curve, even if not necessarily in space. It'll cause things to curve in space-time, as with an apple like falling straight from a tree or something on Earth. Even though it moves in a straight path in space, it moves in a curve in space-time. So what if you don't like apples, right? And you want to try this experiment with a different object, like a bowling ball, say, because bowling balls are cooler. I don't know. I don't like bowling very much, but I'm sure someone does. So what'll happen if you do this experiment again with a bowling ball? Well, based on what we have observed in practice and actual physics experiments, the exact same thing will happen. The bowling ball will speed up if it's on Earth, and a bowling ball in space would just travel in a straight line if it was far enough away from planets and stars and anything that could pull at it, I guess. So gravity is sort of interesting because it'll actually cause a bowling ball to fall at the same rate as an apple would fall, or it'll cause the bowling ball to speed up at the same rate. So I don't know, let's say here's your apple experiment. And you try it again with a bowling ball, which is heavier. But despite the fact that one is a lot bigger and heavier than the other, you'll find that they speed up at the same rate. So you could drop them from the same height. And you can make a very pretty diagram. So this height. And based on what we've observed about how gravity works, it'll speed up the apple and the bowling ball at the same time. So the idea is that you could swap one out for the other, but the curve that gravity causes will look exactly the same. Now, what about a planet in space? You might expect a planet in space in the absence of gravity to move in a straight line, right? But we know that planets don't move in straight lines. They move in orbits. And that's because they're moving under the influence of gravity. So, I don't know, this is a neat planet. It's got zigzags or something. And orbits are generally elliptical. So they look something like this. And the planet will orbit a focus. So if you try your snapshot experiment with a planet, I'll make it a different color. You'll get snapshots at these points in time. Planet will speed up as it gets closer to the focus. So there's probably like the sun or some star or something. They'll be more spaced out as it gets farther away. Now, what would happen if we took this planet and we replaced it with an apple? Or let's say we took an apple and, oh, and actually another point I should make here is that an orbit is also curved, just like the curve that an apple makes in space-time. But this time, it's curved in 2 dimensions of space. So I guess we have y, and we have x, and you can see it's curved in space. But because the planet is speeding up and slowing down, it's also curved in time. So if you just took 1 dimension, let's take y again. And you would get a pretty similar looking curve. Maybe not exactly a parabola. Something a little different. I don't know, something weird. But the point is, it's still a curve, and that's because of gravity. So what if you repeat this experiment? Well, okay, an orbit's not really an experiment. What if you swap out the planet with an apple? Well, we saw that gravity didn't really care whether we were dropping an apple or a bowling ball on Earth. And gravity doesn't care whether it's a planet or an apple orbiting the sun. So if we put an apple here, then it would follow the orbit of the planet. And if we replaced Earth with a bowling ball or an apple, then that apple or that bowling ball would follow the same orbit because gravity doesn't know the difference between them. It just makes things curve, or it just makes things move on curves. But it doesn't matter how big the object is or how much mass it has, or I don't know what color it is or anything like that. None of that matters. Gravity will act the same. And this is a little strange, but this is something that we observe in practice. For example, you can look at the asteroid belt around the sun. The asteroids are different from each other. They're not all the exact same size or shape or weight, or, you know, they vary, but they all have relatively this, like, almost the same orbit. So gravity is treating them all the same, even though they have different sizes. And you don't have to take my word for it. You might have heard of this experiment if you're in a high school physics class. They bring this up sometimes, where you drop a feather and a hammer, and ideally they fall and they accelerate at the same rate because gravity doesn't care that one is a lot lighter than the other. And this doesn't work on Earth because air resistance will make a difference, but on the moon, here's what we expect. Let me play the video. Yeah, how about that? So this is pretty weird, right? Because this isn't how we really expect things to act from our everyday intuition. It's a lot harder to throw a hammer than it is to throw a feather, right? So you wouldn't expect gravity to have this uniform effect on objects, but it does. And this sort of suggests that this sort of suggests a framing for how we should think about gravity. If you've taken a high school physics class, you'll learn that objects with mass each have their own gravitational field that other objects move in, and it depends on an object's mass. But gravity will move an apple in a bowling ball or an apple on a planet the same way. So this sort of suggests that gravity is basically a background stage that all objects are influenced by equally. And this is sort of the motivation for all of general relativity, as we'll see in what Nicholas and Isaac will have to share with us. So it's a simple insight, but it has deep consequences. Oh my God, this happened yesterday too. All right. So we have our first discussion question for you, and we'll put you into breakout rooms to answer this in a bit. But let's say you wake up one day and you're stuck in an elevator. And how you got there, you have no idea. So your first instinct would probably be to push all the buttons or try to beat on the door or something like that. And so you do that and that doesn't work. And eventually you take out your pen that you happen to go to bed with because you're a huge dork. So you take your pen out of its nice little shirt pocket or something, and you let it go and you notice that it's floating and it's not falling like you would expect it to. And then you notice that you're also floating. So you're not standing on the ground either. It's a little weird. I don't know. It could happen one day. So our question is, can you do something from inside the elevator to tell where you are without any information from outside? Just you and maybe your pen, or maybe instead of a pen, you have an apple. I don't know. We'll put you into breakout rooms to talk about this. Where could you be? All right, is everyone back? So let me get my notes out. What you'll have found, or what you'll have been guided to, is that there are two possibilities here. Either your elevator is out somewhere in space, away from heavy things like planets and stars, and it's either just stationary or moving at a constant velocity somehow. And that's a perfectly fine possibility. But you could also be on Earth and you could be falling under the influence of only gravity. So you could be like in an elevator chamber and maybe the cable snapped and now you're in free fall. So both of these could be the case. And there is nothing you can do inside the elevator to tell whether you're in space or whether you're on Earth. So you would need information from outside to figure this out. Like you would need somebody looking at the sky with a cell phone or something. But the point is that locally, inside the elevator, you can't tell the difference. Now here's our second question. You get very unlucky and this happens to you twice. So the second time, you wake up in an elevator and you have no idea how you got there. And this has happened to you before, so you don't even bother pushing buttons or banging on the door this time because you already know that it's not going to work. But something is different this time. This time, it feels like there is gravity because you're standing in the elevator and not floating. And you take out your pen again and you let go of it. And instead of floating, it just falls to the ground. So can you tell where you are this time? Again, only with information from inside the elevator. So we'll put you back into breakout rooms for this. All right, so does anyone want to share their answer for this question? you can either talk or you can put it in the chat. But before I say anything, I want to hear from you guys. Okay, so acceleration. This could be a case. They're either on Earth with no acceleration or in space accelerating up at g. Yeah, again, there are two possibilities here. And either you're on Earth and you're moving with a constant velocity. So you're on the ground, or it's like a hybrid train elevator and you're like moving on a trail, like a railroad track or something at a constant speed. I don't know. But either you're on Earth and you're not accelerating, or you're in space and the elevator is accelerating. So it's like a super elevator with engines or something for some warped reason. And just like with our other scenario with you floating in the elevator, these two possibilities are indistinguishable from inside the elevator. So no matter what you do or how you throw your pen or what you think of as an experiment, nothing you can do will tell you whether you're on the Earth or in space, which sounds acceptable, but it's very profound. So let me get my notes out again. So I guess here's our scenario that we've covered, or here, just to recap. Here, this is all right. So I guess here is elevator number 1, which is on Earth. And here is elevator number 2, which is in space somewhere. So there are stars, so that's how you know it's space. And so we found that it doesn't matter what's happening in the elevator. Like, you could be floating or you could be standing in the elevator. But either way, there are two possibilities. Either you're on Earth somehow or you're in space somehow. And there is no way to distinguish which one it is in either case. So I guess we have like 4 possible scenarios total. Let's say this is the one where you're stationary on Earth, so you're not moving. I don't know, you're on a table or something, elevator table, sure. Or you could be accelerating in space. All right. Or your elevator could be in free fall. Oops. Actually, okay. You should be floating. All right. So your elevator could be in free fall on Earth, or you could be just floating in space. Just vibing, I guess, as the kids would say. So from inside the elevator, you can't tell whether you're on Earth or in space, either way. And you can't tell whether you're in another planet's gravity or not, just based on things you could do in the elevator. So one of the reasons that Einstein is so famous is because he saw these pictures. All right, I really want to say these two pictures, even though I drew four. So I guess he saw these pictures, and he proposed that they're actually the same picture, which is a very bold statement. He proposed that being under the influence of a gravitational field is equivalent to experiencing an acceleration. And in physics, we call this the equivalence principle because, well, it's stating that gravity and acceleration are in some sense equivalent. Like, you'll expect the pen to behave exactly the same way in the Earth elevator that you would in the space elevator. So for all intents and purposes, they're actually indistinguishable. So they might as well be the same thing. And this sounds a little intuitive, even though it's a bold statement, but it makes sense if you're only thinking about, elevators and what your pen will do. But if you look at a few more situations, you'll find that there are some very strange side effects to treating gravity and acceleration as basically indistinguishable. And in our next discussion question, we're about to see one of those weird side effects. So here's our third discussion question. And I'll try to draw this out for you. So here is time. Let's say you're in a rocket ship that's speeding up in space. Or, yeah, let's just say it's speeding up in space because that's where rocket ships belong. And you have a laser. So, and you're just standing on this platform, I guess, and you have a laser. And you're aiming for a bullseye. So you aim the laser at the bullseye and you shoot it, hoping to hit it for your space target practice. So what will the light actually do? Will you hit the bullseye or will you miss? And what if you do this on Earth and the rocket isn't moving, but there's gravity? So what do you expect to happen in both of these cases? I don't know. So where will the laser be like 2 seconds later? Something like that. We'll put you back in breakout rooms to think about this. Okay, so hopefully what you found is that the laser does something crazy in each case. So let me try to draw this again. Here's your rocket that's accelerating. And you shoot the laser from here at the bullseye. And let's say that's 1 second. Then at 2 seconds, rocket has moved a little bit up. So the light would be here. And after 3 seconds, move this box out of the way. Okay. So I'm exaggerating a bit here what exactly it will look like, but the light will miss the bullseye. And if you're in the rocket ship and it's accelerating, then it'll look like it's falling. And if you do this on Earth and you're not falling, or you know that the rocket ship is not accelerating and there's just the Earth's gravity, well, from the equivalence principle, we found that acceleration and gravity are indistinguishable locally, at least. So you expect objects to behave the same way in either case. So on Earth, you expect the laser to do the exact same thing. It'll actually miss the bullseye, which is not at all how we're used to light behaving in our everyday lives, right? You know, lasers are like famous for always traveling in straight paths or something, I guess. And since light is massless, you don't expect gravity to have any effect on it. But as we pointed out earlier, gravity doesn't care how much mass something has. And with general relativity, we find that it doesn't care if something even has mass to begin with. It'll still cause light to curve, just like it would an apple or a planet, which is, this is crazy if you think about it. Like, if you're at home and you're playing with your cat with a laser and you aim it at a wall, you expect the laser point to be exactly where you aimed it. So it is being affected by gravity on Earth in reality, but the effect is so small that you won't be able to see this just by things that you can do in your everyday experience, or like the things that you have the technology to do in your everyday lives. So this is a pretty hard thing to believe, but it does sort of support the perspective that general relativity proposes for gravity, that instead of being something that objects with mass possess and exert on other objects, gravity is more like a background that all objects are influenced by, for some definition of object that includes light. So it makes a little more sense from this perspective of gravity being a universal thing. So in physics, we call this effect of light curving under the influence of gravity gravitational lensing. And the idea is that because of the equivalence principle, acceleration, light's trajectory in an accelerating rocket ship would look curved. So by the equivalence principle, light's trajectory under the influence of gravity will also look curved. And you can see what this looks like in practice, first of all, with this animation that's simulated, and also with real photos that we've taken of galaxies in space. So the bottom two are actually photos taken from telescopes. So this is a documented effect. And the top one, what's happening in the simulation is we have a black hole, which has about the strongest gravity that you can get in the universe. And there's a galaxy moving behind it. And what's happening is that as the galaxy passes behind the black hole, what you would normally expect is for the black hole to just obstruct the light from the galaxy. So you'd expect it to just cover it up. But instead, what happens is because the gravity from the black hole is so strong, the light will actually be curved around the black hole. So I can draw this out to make it a little more clear. Let's say this is your black hole. And this is a light ray from your galaxy that's behind it. And what will happen is it'll curve around the black hole. So you'll actually be able to see what's behind it. And this is very strange, right? Again, because light is massless. And this isn't how light behaves from our intuition. But this is just a very strange consequence of general relativity. And now I'm going to pass the mic along to Isaac, who can tell us more about the perspective of gravity being a universal thing. So take it away, I guess. Oh, I'll stop sharing my screen. Okay.
Thank you. The thing we now want to explore is the perspective that Einstein used basically to take this like simple idea that maybe gravity is not so much about like a force that acts on objects, but rather something that happens to the background that these objects move through, or that like everything moves through. Because we saw this happens with light, not just with like things that we normally think about, like apples and planets. So I think one of the cool things that Einstein did was use thought experiments to come up with general principles or general ideas for what should happen. And so we're going to sort of just go through a couple examples of like maybe what like a path Einstein could have taken to come up with the general theory of relativity, which is one of these, you know, it's like a monster of a theory. It's incredibly complicated, but Einstein arrived at it just one step at a time. So the first thought that Einstein had was something that even Newton could have known about. And Einstein realized that if there were no gravity in the universe, what would happen? Well, objects would travel in straight lines. So if you take an apple, but you just fling it through space, it will travel in a straight line in both space and time, as we saw before. So, you know, we sort of have this picture that Sarah drew of the apple moving in a straight line in time and space. But Einstein also noticed that when gravity is acting, then we see that there are crazy things that can happen, but they all share one thing in common, that there's always some kind of curvature that happens, whether it's in space and time, there's a curve, or in space and other space. So for example, in the orbit of a planet around a star, we see this curvature in space and space. And Einstein also recognized the fact that all of these like objects behave the same. So the paths that objects take don't depend on the properties of the objects. And so this motivated Einstein to think that what we're talking about, rather than just being a force on objects, maybe that like these objects are really just following like, you know, this universal path that all objects would follow. And thinking about the fact that objects travel in straight paths in the absence of gravity, Einstein was sort of wondering like, well, maybe instead of the objects themselves curving, maybe the objects are moving on paths in some like curved background, which is causing them to look like they're curved. And this is sort of, maybe this idea is right, maybe this idea is wrong, but it's basically all of the connections that Einstein drew that help us understand why this is such a compelling idea. And so now we're going to kind of go through basically the steps. And the first thing to recognize is that this idea that objects move in straight paths in space and time when they're not acted upon by gravity. And Einstein said, well, if gravity isn't really a force, like it's not acting in the same way that other forces do, like pushing a bowling ball versus pushing an apple, then maybe these objects are actually moving on straight lines, because this is what Newton said. Newton said, when objects are not acted on by forces, they move in straight lines. And so we're going to kind of explore this idea of what it would mean to move on a straight line if the background were curved. So first of all, what does a straight line mean? Well, on a plane, a straight line is just, we have lots of experience with it. It's the shortest path connecting 2 points. So what Einstein thought is maybe in general, what we want to talk about is the shortest path between 2 points. Because if you think about a curved surface, so you're thinking about maybe a surface we're comfortable with might be the Earth. There are no really straight lines on the Earth because, you might think, oh, you can take a straight path through the Earth. But if you're stuck on the surface of the Earth, like most humans are in our everyday experience, you can't take a straight path between any 2 points because the surface itself is curved. So Einstein needed to come up with a way to generalize the idea of a straight line path, a path that's not being acted on by any forces. So what he came up with is the idea of what we call a geodesic. And a geodesic is a fancy word for the shortest path between 2 points. And this is exactly what we saw straight line paths were in a plane. They're the shortest path. So Einstein is saying, maybe the reason that objects travel the way they do in flat space or in space without gravity is that they're really following the shortest path between two different points. And so now we're going to do a thought experiment to try and sort of understand the properties of these geodesics on the surface of the Earth. And a lot of Einstein's thought experiments involved trains. So we're going to also do a thought experiment involving a train. So you're on the surface of the Earth. Maybe this is a view you're comfortable with. We have these lines of longitude that go from the North Pole to the South Pole, and then we have the equator, lines of latitude. And you're standing somewhere on the Earth. And it's almost Christmas Eve, and there's a train track that runs north. And as far as you can tell, it looks like it's traveling in a straight path. And it looks like it's traveling straight north. All right. And all of a sudden, a train comes riding along on the train path, and it stops, and the conductor tells you, well, it's time to get on because we're going to the North Pole. This is the Polar Express, right? So my question for you is, what is the fastest way for the train to get to the North Pole? If it wants to get there, it wants to get there before like 12 o'clock on Christmas Eve or something. Where should it go if you're starting here and trying to get up here to the North Pole where Santa Claus is? What path should it take? Because there's no straight line path, but there is a shortest path. So does anybody have any thoughts about what kind of path it should take? Maybe I'll give you like 15 seconds. Oh yeah, people can just like create a wormhole. That's clever. I guess this is what Santa would probably do. Yeah, so along the longitude line. So we sort of drew these lines out for a purpose. So this line of longitude, and we sort of understand why. Because if you stand on this line of longitude and hold the compass in your hand, it'll point straight north. And if you go straight north along this line of longitude, basically you'll stay on the line of longitude. All right, and this is actually the shortest path. And on a sphere, so the Earth is a sphere, or basically a sphere. There's a special name for these geodesics that are also the shortest paths. They're called great circles. And they're called great circles because they basically travel all the way around the Earth. So if you continue this line of longitude, it'll run through the South Pole, all the way back around, back past the Earth, through the North Pole, and then through your starting point. So wherever you're starting your journey from, the Polar Express. And these are the shortest paths on a sphere, which kind of sounds weird because they're called great circles because they wrap all the way around the Earth. But it turns out that if you take 2 points on this circle, then the shortest path is the arc of the circle, it's called. So the arc means this part of it, this little place. This arc of the circle is the shortest path between the 2 points. So between the North Pole and wherever you are right now, there's a great circle, and that great circle is a line of longitude. And this concept that there's a shortest path between 2 points on any surface means that, well, the way that Einstein interpreted it as saying basically like, this concept is okay. It's possible that objects follow straightest paths or follow the shortest path because in general, if it were the rule that objects should travel on the shortest path in curved spacetime, then there will always be a shortest path for them to follow. And there's sort of another like way of thinking about how to find the shortest path in general. And the best way I think to explain it is to think about if you had a compass and you were just trying to get to the North Pole on your own. If you had a compass, you're trying to get to the North Pole on your own. What you would do is you would follow the compass needle. And the way you can tell that you're on the shortest path, even though you can't have any notion of like what a straight line is on the surface, you can tell you're on the shortest path because your compass needle doesn't change as you move north. Basically, as you take each step closer to the North Pole, the compass needle keeps pointing in the same direction. And this is like, it's sort of a heavy-handed analogy. There's some subtlety, but in general, this is what the definition of these shortest paths are. Basically, like as you move, your direction doesn't change, even though it does look like it's changing, right? Because here you're sort of pointing in that direction, and when you're up here, you're pointing in a different direction. But from your perspective, your direction isn't really changing, right? You still think you're traveling in the same direction because you're moving along the surface. Does anybody have any questions about this? This is kind of a complicated topic, but all right. And so now I think we're going to take a short break. I'll clear the screen just to let everybody have a chance to get, I don't know, a snack or I don't know, whatever. So we'll maybe take like a quick 7-minute break or something. And in the meantime, can feel free to play around with this this link here, which is sort of a fun tool that it helps you sort of visualize like what shortest paths look like on the Earth when you project them onto maps. It can be kind of crazy. It might not be what you expect. So feel free. So what time is it? It's almost 2 o'clock. So we'll meet back at like 2:07 or so. And we'll be around here for questions too. So. All right. Hey, everybody. So I'm going to get started again. I think this animation or this website is just kind of fun because it can kind of show you just like a picture of how maps can kind of distort our perspective. So this is just a sort of a cartoon of if you wanted to take the shortest path between Delhi and India and Urbana in Illinois, where would you go? Well, you sort of think you might want to take the shortest path, but if you just took a straight line path on a map, it would actually end up being quite a bit longer than what looks to be quite a bit like curvier, this actual true shortest path, which goes pretty close to the North Pole. So that's just something to keep in mind. Like maps can distort our perspective. So sort of have to be careful when we're talking about these curved surfaces, especially about the Earth. All right, So now we're going to move on. So we've been talking sort of about how the Earth is curved, and we we sort of have this idea that we can find the shortest path between 2 points on the Earth. But how would we actually go about figuring out that the Earth was curved if we didn't know? This is sort of a very important question, because there are still some people on Earth that don't really believe the Earth isn't flat. So maybe we can come up with some ways to convince people that, first of all, that the Earth isn't flat, and second of all, maybe we can find a way that also measures the size of the Earth in the process. This is kind of a sort of fun bit of, like a little math problem or something. But yeah, we'll go back into breakout rooms and just sort of discuss this for a little bit. There's a famous example for people would see the tops of ships come over the horizon before the bottoms of ships, which is an indication that the Earth is curved. And you could also use this to measure the curvature of the Earth by designing a clever experiment. So then the last thing that I sort of want to discuss here is, what would it be like if the Earth were much, much smaller? Do you think it would be easier or harder to convince flat earthers that the Earth were round if the Earth were much, much smaller than it is now? Maybe we can all just like throw an answer in the chat. Easier or harder to convince flat earthers? Yeah, so most people agree that it would be easier because what would happen is that like basically all of the effects of having curvature would be amplified. So all of the things we talked about, like when ships went over the horizon, it would be like, just like 15 feet in front of your face, you would see like a ship just like fall out of your field of view. So all of these little things would amplify. And the big idea here is that Einstein realized that in order to measure curvature of something, you really need to, it's really a non-local thing. So what does that mean? It means you can't do an experiment like right where you're sitting. Like you can't just like look right in front of your face and figure out the Earth is curved. You need to like really like sort of have information from two different places. And the further away the places are, the better it is. And further away compared to what? Well, the idea is that there's this like the radius of curvature, as it's called, which characterizes the like how curved an object is. So for a sphere, the radius of curvature is just the radius. So the further away your like different experimental machines are, so you have like two people, Alice and Bob, like designing an experiment, they can figure out the Earth is curved better if their relative distance from each other is larger compared to the radius of curvature. So you can sort of imagine why this is true, because the further you go, the more curvature starts to take effect. So it's really like the effects of curvature are really a non-local thing. And locally, you can't tell that the Earth is not well, you can like, so if you just look at like you have the experience of going outside and like the Earth seeming flat. So you really need to go a long distance away on Earth to figure out that the Earth is curved. These effects really start to only matter at big distances. I think I'll skip this next slide because of time. It's kind of a fun thing. You can look up videos of Hyperbolica, which is like a game that lets you simulate what it would be like to be in curved spaces or whatever. But I'm going to move on to just a discussion of space-time. Oh, sorry, this did not click forward. Sorry, yeah, Hyperbolica. Oh, okay. 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 So this is Einstein's real insight, that we're trying to like characterize gravity in terms of curvature. And we understand that objects should be following straight line paths in the absence of forces. And if we think that gravity isn't a force, if you think gravity is just acting in the background, then we think that objects should be following the equivalent of straight line paths. So we think objects should be following straight line paths, but there's no straight lines in curved spacetime. So objects will follow geodesics in curved spacetime. It's the idea. And the main thing that Einstein saw is that, curvature only matters over like non-local things. So before we saw this example where if you're stuck in an elevator, it's very hard to tell whether or not there's gravity. And Einstein says, aha, this is because gravity is an effective curvature. And curvature, you can only really realize by looking at things far away from you. You have to be able to look at things far away. And when Einstein thought this, he meant far away in space or far away in time. So that's why the elevator it's so hard to tell what's happening, because you can only see what's right in front of you. Whereas you really need information from further away, because the effect that's causing it is curvature of space-time, which you need to know non-local things about in order to figure out. And so now I'm just going to introduce a little bit of language that people use to talk about space-time, because it's so common. So when people talk about space-time, they usually draw these diagrams, which are called space-time diagrams. So for better or for worse, people have decided that time will go on this axis and space, which is often called something like X, will go on this axis. This is opposite of what most people experience in physics classes or math classes. But the idea is that just like points in space, for example, the North Pole and where you are now are points, there can be points in space-time. And these points in space-time, so this is a point, that's a point, these are called events. And why are they called that? Well, because this is sort of like a point in space-time is a particular point in space at a particular point in time. So it's called an event because you think an event happens at a certain place at a certain time. We need all of this information to characterize where it is. Now, you can also have what's called an observer in space-time. And this just means like an object or a person or anything floating through space-time following a certain path. So this just means the object is moving in space and time, just like we saw before with the example of an apple. So in this case, we would draw, it would look something like this, the curving apple in space-time, because now a diagram is turned sideways. The idea is you take a path through both space and time. And the important thing to notice here is that there are many different paths between two different points in space-time. And just like many different points in space have, if you travel between two different points in space, you do not have to travel the same distance. Einstein says there are many different points in space-time, or there are many different paths in space-time through two different points, and not all of them will follow the same distance through space and time, which is one of the first reasons he thought that time is maybe not as absolute as we think it is. And the other big concept here is that there is the way we see a geodesic in space-time is a geodesic is just one of these paths. And in particular, it is the path that an observer will follow if they're just left to, if they're not acted on by any outside forces, including, we think of gravity not as a force, but so a geodesic might be curved because of gravity. It might do something weird in space-time. If you imagine that, like we said before, this is maybe a flat projection of an actual curved space, things might look wonky, but the point is that there is a shortest path that objects will follow. There's a single shortest path that objects will follow. And that's why we're comfortable with this idea that objects are following shortest paths, because we know that objects do something. If you drop an apple in space, it will do something. And it won't do two different things. It'll do just one thing. And so that's why this idea that there's a unique shortest path is so such a good idea. And I think now I'll let Nicholas take over, and he'll start talking about how gravity causes this this curvature that we see in space-time.
Thanks, Isaac. Give me a second. Oh, can my other computer be made a host? I actually can't share. me a second as well. Okay, let me try again. Thank you. Okay, so let's go back to the slide where we were. Okay, so so far we've talked about this idea that gravity is fundamentally an effect of curvature of not a two-dimensional space as we were talking about in the case of the surface of the Earth, nor a three-dimensional space, which is what we're often used to talking about, but actually a four-dimensional space-time where the points are events. But one question still remains to be seen, right? So gravity is caused by curvature, but we have this intuitive notion that if we have, if we think about the gravity due to, let's say, me or an apple, that's so much weaker than the gravity which is due to the Earth, which is felt by everybody, and that in turn is much weaker than the gravitational field due to the sun, which is able to keep all the planets in orbits for billions of years. And we asked the question, how come it is like, how would we articulate that that gravity should be stronger around something like the sun versus something like the Earth or something like me? And I think it's pretty clear to say, and something that Newton already knew, is that gravity or the gravitational field of something is larger if that object is more massive. In other words, if we think about gravity as curvature, we ought to think that the curvature of space-time is related to the amount of mass or that there is. And more specifically, we could also say that that means the amount of energy, because by E equals mc squared, which was something that Newton said. So this is, sorry, E equals mc squared is something that Einstein said that is a relationship between mass and energy, and basically the statement that like mass and energy are fundamentally, equivalent quantities. We sort of, come to this conclusion that if we increase the amount of mass somewhere, we increase the curvature. So, sorry, I'm on the wrong slide. Okay, yeah. And so this is sort of succinctly summed up in the quote by the famous physicist John Archibald Wheeler, which is that space-time tells matter how to move and matter tells space-time how to curve, right? And so this is sort of elegantly encoded by Einstein into what are called the Einstein field equations, which are the following. And so I think a few questions come to mind, especially when I look at this. And I guess one of the first questions that I would ask is, Nicholas, you said this was the Einstein field equations. How come there's only one equation without an S? And the reason is that this actually is multiple equations. It turns out to be, when we get down to the bottom of things, this turns out to be 10 different equations, and it turns out to be quite complicated. And so even though, the basic ideas of general relativity are very beautiful, and it's been considered one of the most beautiful theories in all of physics, it's such a complicated theory to solve that even just doing the math of general relativity turns out to be a research topic. And it's at the point where you could learn the math of general relativity, and if you were fluent in that mathematics, then you could actually make meaningful contributions to the cutting edge research of general relativity. But this, expression looks a little bit complicated and a little bit opaque. But what it actually means is pretty simple. So the left hand side is something which we call the the Einstein tensor, but you can sort of think of it as the curvature. And then the thing on the right is something called the stress energy tensor, but you can sort of think about it as the mass or energy, which is somewhere. So we sort of intuitively, whoops, this is not good handwriting. We sort of intuitively understand what this means, which is that if I increase the amount of mass or energy somewhere, I increase the amount of curvature, which is sort of what we were wanted to say before. And one reason that we find, general relativity to be so plausible is that from this geometric perspective, we're able to obtain many familiar observations. So even though the paradigm here is fundamentally different, we're thinking about geometry instead of forces. Like gravity, like as a force doesn't really exist so much as, as an artifact of curvature in space-time. Regardless of how different those pictures are, we still are able to describe things like falling apples or the orbits of planets, just as well, and actually, as we'll come to see, even better. And so that sort of convinces us that at least it's plausible that general relativity ought to be true. But there are other consequences, because if they're of general relativity that aren't in Newtonian mechanics, things like gravitational lensing, but also other effects which are also quite counterintuitive, which is just as well because it's nice to be able to test our theories. And so as Isaac had said before, if we imagine a three-dimensional space, or sorry, just a space, let's just draw a two-dimensional space actually. If I have two different points, a start point and an end point, and I draw, multiple different paths between them, I think, to us, like three-dimensional creatures, it's pretty intuitive to us that these paths don't have to have the same length. Like, even though we start at the same point and end at the same point, we need not have, travel the same amount. Like if Isaac, Sarah, and I both start from the same place and end at the same place, some of us might be more tired than others just because like we don't have to have walked the same distance. And once again, to reiterate, Einstein's critical insight was that now, I should say let's say this is X actually, and this is T. Einstein's critical insight was that you can start from a point, you can end at a point, but you can take multiple paths in space-time from one point to the other. You don't have to, you do not have to take the same path. And consequently, you do not have to, take the same like length of path through space-time. And some notion of the length is related to how much time you experience. So time dilation is this phenomenon that different observers can, start from the same point, sort of take different trajectories, and then end up back at the same place at the same time and not agree about how much time has elapsed. Now, you might speculate rightly that this effect is pretty low because in everyday life, we take different paths all the time and we never really disagree about the time because, it's just not that big of an effect. But it is something that is, as it turns out, pretty relevant to the workings of everyday society. So, for example, you might be familiar with this idea of GPS, which is predicated on the function of many satellites in geostationary orbit above the Earth. And, it's quite critical, for just knowing where you are in general. But there was, believe it or not, a time where it didn't exist, and also a time where people wanted it to exist. And so a bunch of engineers, came together and they designed these very, beautiful, pieces of technology. But one thing that they didn't quite believe physicists on was that general relativity was real. So what they did was they put in a sort of a computational switch in the satellites they sent up, saying, okay, well, if we press a button, then like the satellites will correct for general relativistic time dilation. But otherwise, we'll just ignore it. It turns out that when they ignored it, the GPSs would quickly lose sight of or lose, the positions of, their devices, and you basically wouldn't be able to track your position for very long before the error started accumulating. But they found that once you actually, turned on that switch and you started making those very tiny corrections to the amount of time experienced by the satellite and the difference between that time and the time of people experience on Earth, they found that they were able to, achieve the great successes that we are used to with GPSs today. The ability to track people to like closer to like less than a block. And you might ask how much of an effect that really was. And it turns out that it's not a big effect at all. Earth satellites actually only differ by our clocks on Earth by 1/100th of a second per year. So if we wait 1 year, then our clocks only go out of sync by 1/100th of a second. But it turns out that the precision required to do GPS is so incredibly, stringent that amount of error is actually quite a bit. Now, to be a little bit more extreme, if we go to, or like to something around the sun, if one of you would like to volunteer to go to the sun and just hang out over there, it turns out that that effect is more like 1 minute per year. So if somebody, goes to the sun, hangs out there for a year, comes back, there will be they will like disagree about how much time has passed by about a minute. And so that's an amount of time that I think we can understand, even though on the grand scheme of things, it's still small. But you can imagine if you're around something very extreme like black holes, which we technically don't know about yet here, then this effect can potentially be extremely large. Okay, so speaking of black holes, let's figure out what these are now. So black holes are one very curious effect of general relativity, or a curious prediction of general relativity. I think one misconception people have about black holes is they sort of think that Einstein wrote the theory of general relativity with the idea that it would have black holes in it, but actually Einstein didn't expect there to be black holes in general relativity and was sort of disturbed by their presence. He sort of speculated that maybe they might be a mathematical, sort of quirk of the theory that would never happen in practice, or maybe it was just something very mathematically strange that wasn't physical. But it turns out that black holes do exist. So what are they exactly? Well, they're fundamentally these very extreme regions of high gravity where by definition light cannot escape. Hence the terminology black hole. Because light can't escape, it turns out that means nothing can escape, because if you think about it, light is the fastest traveling thing in the universe. And if light can't travel fast enough to escape, then neither can anything else. And I think this is like particularly interesting because this means that nothing in the black hole can ever escape or even influence anything on the outside. Something falls in, it's lost forever, and nothing it says will ever make its way to anything outside ever again. And one thing which was interesting is, as I've said, Einstein even thought that even if these things existed, they probably wouldn't actually form in nature. But it turns out that some scientists actually demonstrated that they can. And in fact, one Nobel Prize won last year was won by Roger Penrose, who demonstrated mathematically that not only could they form in nature, but it was pretty natural for them to do that. And I think there is a pretty nice intuition for this, although this is a little bit hand wavy. So you can imagine that in Newtonian mechanics, which is sort of like the theory of gravity that you learn in AP physics and is quite a bit simpler. You sort of imagine that if I have a star, which is a ball of gas, and the star runs out of fuel, what's going to happen is the star contracts and it contracts and contracts, and the core heats up. And it heats up so much that the particles in the core sort of bounce around more. They increase the pressure. And in Newtonian mechanics, you can always squeeze the ball enough so that the pressure can hold up the star again. So even if the fuel runs out, something else is going to hold it up. However, in general relativity, this doesn't really work because we know that E equals mc squared. So energy also has gravity. So when your star collapses, yes, the pressure can go up to hold up the star, but what really happens is the pressure also feels gravity. And so you're increasing the pressure to hold up the gravity, but you're just getting more gravity. And so there comes a point at which this becomes a runaway and you just end up with a black hole. You can't increase the pressure anymore to prevent that collapse. And so I think this is a pretty interesting insight. But do these things actually exist? Well, people have known about black holes for a long time, because essentially what you do is you look for things where like you expect there to be something very heavy, but there isn't anything. And one of these very famous examples is this animation on the left, which is not an animation so much as a movie, because this is actually like, these are actually observations taken over about 20 years. You can see that these dots are all stars, which are spiraling around the center of our galaxy. But they're orbiting, you can see this invisible point. So like these stars are moving close to the speed of light. This one's moving at a few percent of the speed of light when it gets to, that's the fastest point. But you can't see anything there. And this is actually something which was noticed by the team of Andrea Ghez at the University of California, Los Angeles, and won her the Nobel Prize last year as well. And it demonstrated that our galaxy has a black hole at the center, which has a mass of about a few million solar masses. So just imagine a few million suns crammed into a very small space. And a little bit more recently, a team led by a few people across the world have demonstrated that you can actually take pictures of certain black holes. In fact, this black hole is the supermassive black hole at the center of an elliptical galaxy called M87. And rather than being a few million solar masses, this thing is a giant. It's actually a few billion. So you can imagine that's that's like 1,000 times more massive than ours. And basically, people took this picture by putting telescopes all across the entire world and basically turning the Earth into a gigantic telescope. And so I think we can say beyond reasonable doubt that if black holes didn't exist, things which behave very much like black holes exist. So I think it's pretty natural to assume that they do. There are other predictions of general relativity which have also gained a lot of observation power recently, which is one of which is this idea of gravitational waves. So gravitational waves are essentially like ripples in space-time, you can sort of imagine. So if I take some mass and I sort of wiggle it around, I will cause a disturbance in space-time, which sort of propagates, in fact, at the speed of light. And so there's sort of an intuition for why these gravitational waves have to exist. Like if I change the gravity at one point, I sort of disturb the space-time, but like space-time farther away needs longer to realize that it should also be disturbed, because we're fundamentally talking about the smooth shape of space-time here. And the reason why they travel at the speed of light is simply because they can't travel any faster than that, right? Like if they did, then they would violate causality. You'd be able to send messages back in time and shoot your own grandfather and all of these things we don't like to think that can happen. And it turns out that in 2015 we actually directly detected gravitational waves, although we had known about them for a while. And one of these these gravitational waves that we detect are due to very large black holes, about 40 solar masses, colliding with each other and sort of releasing these like gigantic, explosions of energy across the universe in the form of gravitational waves. It turns out that the first gravitational wave event ever detected was between two about 40 solar mass black holes. And when they collided with each other, the gravitational waves took away about 3 solar masses of energy. So just imagine taking E equals mc squared, taking m and replacing it with 3 solar masses and turning that all into energy. Just imagine the entire sun being turned into pure energy and imagine 3 of those being taken away. That's how much energy was released by this collision. And it turns out that a typical black hole merger of this kind will, at the time of like the very last point of its merger, when the black holes are closest together, will release more power, so energy per unit time, than every star in the entire universe, observable universe, put together. So that just sort of gives you an idea for the sheer scale of these events, how in these brief moments of time, they sort of, in gravitational waves, outshine everything else in the universe pretty much. But there is another prediction of general relativity, which is not just that we can detect these things, but why they would merge at all, right? So when we have 2 black holes, and Newton would say that 2 black holes or 2 anythings orbiting each other would just orbit each other forever. But the point is that gravitational waves are also responsible for causing things like black holes to merge, because gravitational waves release energy or take away energy. So if you have an orbit, it will gradually shed energy in the form of gravitational waves until the black holes actually have the ability to merge with each other. And so it's sort of elegant that gravitational waves are at once the reason why we know about these events and also the reason why they can happen in the first place. But black holes are not the only thing we can learn about when it comes to gravitational waves. We can also learn about neutron stars, which turns out to be something that Isaac studies at the moment. And it turns out that you can detect the collisions between 2 neutron stars. So what are neutron stars? They're basically when you have a 10 to 20 solar mass star that ends its life, it ends up creating this remnant, this city-sized atomic nucleus, right? So just imagine you take 2 solar masses, 2 sun's worth of masses and cram them into the size of Manhattan, or like the size of a city. And two of these objects colliding with each other, like, also create very loud signals across the universe. And it turns out that these events, it's been determined by astrophysicists recently, are responsible for creating most of the heavy elements in our universe. So if you imagine, if you have a gold ring on your finger, or if you have a uranium bomb in your basement, both of these things are only possible because neutron stars collided over and over again across the courses of the universe and created all of these elements. So I think it's a very beautiful picture to imagine that all the things that we're used to, like in our phone, like in our glasses, like these things are in large part due to a large part forged in like these massive collisions between neutron stars. Okay, so I have another question, a discussion question, but I guess we can sort of just run through it sort of heuristically. We don't have to talk about it in breakout rooms necessarily. But I want to pose this question because I think it's particularly neat. And I'll give you a few seconds to type in chat what you think. But general relativity, as we've mentioned just a few minutes ago, predicts black holes, which are, as we've said, by definition, regions of extreme gravity from which light can't escape. So, so now we take a step back and we recall the equivalence principle. So we said in the equivalence principle that gravity is fundamentally the same thing as acceleration. So if gravity, sort of creates, a region of space where light can't escape from, then what does that imply about acceleration? So I guess I'll give you a few minutes to reflect on this question. Anyone have any thoughts? You can also feel free to mute your microphone if you have any ideas. I think one illuminating question might be, so light travels faster than anything with mass. So basically everything. It travels faster than you, and it travels faster than any ship we could ever build or hope to build. But the interesting question is, does that mean that we can't outrun light? Or do you think that it's possible to keep running such that light can never catch up to you? Okay, so I guess I'll just outline the solution to this puzzle. And it turns out that, the equivalence principle might inspire you to believe that when you accelerate, just like what happens with gravity, acceleration might cause a region of space behind you, where light can't escape from. In other words, it could be that when you accelerate, there's a black hole behind you that follows you. And it turns out that this is in fact reality. This is a prediction of not just general relativity, but actually a special case of general relativity called special relativity. It's basically whenever you accelerate, it turns out that there's this gigantic horizon behind you, like that follows you, and light that starts off from behind that horizon cannot ever catch up to you, no matter how long it takes, right? As long as you keep accelerating. Now, if you stopped accelerating, then the picture is a little bit different. This can't really happen anymore, and the light will catch up to you. But so long as you accelerate forever, it will never catch up to you. And this is called an apparent horizon, sort of an analogy to this concept of an event horizon. Yeah, but I think this is a particularly interesting fact because I think it's a little bit scary that every time you accelerate, you're followed by a black hole essentially. But you need not be too afraid because that distance is pretty large. So if you accelerated at the modest acceleration of 1g, so one gravitational acceleration. So
sort of the acceleration you'd need to simulate the gravity on Earth. If you did that, then the distance that this apparent horizon would be behind you would be about 1 light year. So it's true that if you continue to accelerate this way, that light from farther back than 1 light year could never reach you. But it turns out that 1 light year is quite a long distance. So in practice, it's very hard to detect this, if at all. But I still think it's a very neat idea. Sorry, I just noticed this question. So Max asked, wait, if we're on Earth and the Earth is accelerating around the sun and the sun is flying through space, does that mean we're perpetually followed by an apparent horizon? I think the answer to that question should be, that's a very good question. Yeah, let me think about this. So I think the important thing is that you're also changing direction. So it wouldn't be like light couldn't reach you because the acceleration is always changing as well. But I think, do either of you two have thoughts?
I think it's quite complicated because the actual like solution to the relativistic problem becomes very very mathematically complicated. So I don't exactly know, but I don't think it'll be exactly the same. There'll be some you'll like at this point you'll be like really digging into the weeds of how general relativity works and how light moves in general relativity, which can be quite complicated.
Yeah. So I think it's a difficult question. Sorry. Also, yeah. So another question here. Since most stars are more than 1 light year away, does that mean if we start falling while facing up, we can't see stars? I'm still trying to understand this. I guess the thing is like it's a little bit hard to wrap your head around, because if you start falling and you're accelerating at 1g, that doesn't mean that you won't see stars which are more than 1 light year away, because the light from those stars was closer than 1 light year away when you started falling. So even though like the light that comes from those stars later on can't reach you because it's 1 light year away, the light that you see didn't start off 1 light year away. It started off closer when you started accelerating, right? Like if I started falling now, the light that hits my eyes was pretty close to me already. Like it had made up all of that distance over the past year. I guess that should be correct. However, you'd have to accelerate for the entire time. So you can't like ever slow down. Not only can't you not slow down, but you have to always be speeding up. Which is a little bit weird, because you think you can't speed up forever because of, because there's this finite speed of light, but it turns out you can speed up forever somehow. And it's a little bit hard to wrap your head around, but these are the counterintuitive consequences of general relativity. So I think we don't have that much time left. I just want to say a few more things, and we have one final discussion question. So first of all, there are other consequences that you might want to look into if you want to do a little bit more reading of general relativity that are pretty weird effects. So first of all, light that comes from a place of high gravity turns out to be reddened. So if we were to look at a black hole, if we dropped a friend into a black hole, which is not very nice, we would see that they would slowly, instead of just looking like they fell into the black hole, they would look like they were slowly falling into the black hole until they sort of like slowed to a stop, but the light from them becomes a lot redder and redder and redder, and eventually so red that we can't see them, right? And so this is an effect called gravitational redshift, this idea that gravitational wells, light that comes from them will be reddened when they come out of the wells, And this has actually been measured before for stars that move very close to the supermassive black hole at the center of our galaxy. And there's also this idea of relativistic procession. So I'm just going to draw this really quickly. If you have the sun and a planet, Newton believed that the planet should just move in an ellipse. And Einstein, his theory actually predicts that you don't quite move in an ellipse. You sort of almost move in an ellipse. But then right as you loop around, you sort of miss a little bit. And then you sort of do this spiral pattern, or like this rosette pattern. and I think I'm drawing it, but you can just look at the picture below, which is a little bit nicer. And it turns out people actually knew about this effect before they knew about general relativity, but they had assumed that it was due to like another planet. So they had observed it most prominently in the planet Mercury, and they thought that this was due to the fact that there was a hidden planet called Vulcan somewhere. Now, it turns out that they should have saved that cool name for something else because Vulcan doesn't exist. That planet doesn't exist because this effect isn't due to another planet. These are both, pretty important effects of general relativity. So in this final discussion question, I want to ask like this philosophical question. So unlike before, there isn't a right or wrong answer to this question, but the question is prefaced by the following statement. So the predictions of Newton's gravitational theory are not always applicable in the real world. So, they describe things that we're used to, like falling apples and planets pretty well. But when it comes to extreme things like, black holes, or even just like, effects like gravitational lensing, Newton's physics doesn't really describe that correctly, or even with the same paradigm. So I would like you to discuss in this final breakout room session whether or not you think that Newton was wrong. Hey, everyone. Is everyone back? I guess everyone is back. I just wanted to thank you all for attending this Rainstorm session. I hope you learned something about the nature of gravity and how it's intimately related to general relativity. Oh, thank you for the hat comment. I hope you learned a lot, and we'll be motivated in the future to sort of read or even just think about this a lot more, because it really is a super fascinating theory, and it sort of speaks to the way that physics is done, that we can discuss, like whether or not Newton was actually wrong. We can sort of think about, like to what extent, like physics is just models, and to what extent Einstein's model does and doesn't describe the universe that we live in. But thanks everyone for coming. I think Elia will post a student survey link, but we encourage you to fill it out because we really value your feedback, and would like to know how to improve this course in future years. So thank you all.